All right, so let me tell you where the physics perspective and the chemistry perspective are really different. Chemistry, quantum mechanics tends to be example problem after example problem. Here's a particle in a box. Here's a harmonic oscillator. Here's the hydrogen atom. Here's rotation. Problem, problem, problem. And hopefully you get it pretty well. Okay, here's what physics does. You're going to love this. All right, it's all about something called Dirac notation. Anyone hear of this before? Some of you? Okay, here's how it works. Quantum has integrals. Yeah, I always like teaching Pchem 1 is thermo, Pchem 2 is quantum. I like Pchem 1 thermo because everything's a derivative. Pchem 2, everything's an integral. Quantum, everything's an integral. Integrals are harder than derivatives, even though one's forward and the other is kind of going backward. I always think of integrals as anti-derivatives. That's how I do it in my head. But reality is most people have a hard time with integrals. Chemistry, quantum, does everything, just shows you all the integrals. Physics, they use this set of symbologies, Dirac notation, that replaces most of the integrals with symbols. Symbols that can be manipulated. It's almost like a game. Sometimes these can be fun. Sometimes they can still be pretty hard. So let me give you an example. All right, let's say that you're normalizing. It's okay if you don't remember this. But let's do like particle in a box. And you know that if you do this, let me just write this particle in a box. Check whether a wave function is normalized. And again, we're going to cover normalization in case if you don't quite remember. Okay, but in chemistry, this is, you learn particle in a box. You would learn to do this. Here's the normalization constant. The complex conjugate of sine is just sine, so you're going to end up with the sine squared. The normalization constant squared, dx. And then what I would do is, personally, I would go online and find some software to do this. There's online, Mathematica Online is free. You can download Mathematica from the UIC web store. You might want to do that because there's a couple problems that you might want to have some more advanced. I don't like just doing these like off of my knowledge of calculus. Once I set these up, I get some software to do it for me because why wouldn't I, right? Okay. Figure it out, write it out. Either you know how to do it or you look online. Watch this. You're going to love this. This is Dirac notation. That's a wave function. So what I just did, this is this, and it's automatically 1. Okay, so again, write this out, figure out the wave functions, do some calculus online, or write this and automatically write the number 1. Right, symbols. So you turn all this calculus into symbols, and the symbols have rules. Like when you see this, you just write 1. You don't have to do any of this. Okay, let's do another one. Let's do expectation value, average value of x. And again, if you don't remember this is fine because we're covering it. Okay, so you would have an x, which is just an x. So with the plane, sine 2 pi x over L, that's the ground state, dx. And that would be actually equal to L over 2, by the way. I just went over this class, so I remember it. So again, I would, this is actually 2 over L sine squared x dx. That's what I would put in my Mathematica Online. It would give me the right answer. But the symbology, the Dirac notation is this. And again, there's a special way to solve it. So, which would you rather do, this, or would you rather work with that? Right. So this is what Dirac notation is. We're going to spend about a month learning these rules. So you can kind of see what the notation looks like, how to manipulate them, to know where, oh, okay, that's just 1, or, oh, okay, that's just 0. It's really easy to figure out when is it 1, when is it 0. Most integrals in quantum are just 1 or 0, or h bar. And so that's why Dirac notation is brilliant. It eliminates most of the math. However, I do got to warn you, I know it's like, oh, well, that's so incredibly easy. Why don't we do it that way all the time? The answer is, it actually is a little difficult. Once you get more into it, so there's a lot of rules. It has its own way of being hard, but just not hard this way. And I think that's actually for the best. Okay, anyway, so that's the big picture. But as I mentioned, starting Wednesday, today again is a bit of a blah day. So I just want to cover some historical bits. Starting Wednesday, we're going to start with solving Schrodinger equation for like particle in a box, stuff you did as an undergrad. And kind of quick, make sure that you kind of remember how to do this stuff. And that's your first problem set, so I'm going to be doing stuff in your problem set. Okay, historically, what I wanted to cover is, it's kind of interesting how, I look at a lot of YouTube videos of, Stephen Hawking, his book, his audio book, or people make videos of Stephen Hawking's, like, A Brief History of Time, or Neil deGrasse Tyson's book, Astrophysicist for those on the go. So anyway, it's kind of neat that they always talk about the theory of relativity and how it doesn't mesh with quantum mechanics and with gravity and all this stuff. So one thing I realized is that, in all of your physical science learnings, you cover certain regimes of, certain theoretical paradigms, and that would be Maxwell's equation of relativity, and then quantum mechanics. And so these are like subjects, mostly mathematical, sorry, but these are subjects. These are classes in their own right. Okay. So, of course, Maxwell's equations are all about electromagnetism. So you should have covered this. You should have covered this in usually physics 2. That's what I had, physics 2. And it's all about figuring out your dipole moments, the energy of a, electric or magnetic dipole. Anyway, I'm just writing on down. You may notice this from that little textbook thing I'm writing. It's not good at all, I know that. It's just a very quick synopsis I thought would be, it is free. I'm writing a free textbook, so I sent that to you because it's free. It also represents my own understanding of quantum in a very succinct manner, so I thought that might be just a good way to get restarted if you feel like you've totally forgotten all this stuff. Okay, so Maxwell's equations, these two describe, let's see, that is how a power plant works. Get a magnetic field to rotate and you generate an electric field which generates current. This is an electrical motor, right? Get it to work and get a current flowing through some wires, generate a magnetic field that turns wheels, right? That's your Tesla. This has to do with how the strength of an electric field, assuming that there's no point charges. And this is the same, magnetism and electric fields are the same thing, basically, except magnetic fields are weaker. So notice that those are identical. Okay. All right. And you remember what del is, do you? I know some of you don't remember this stuff. Del is double derivative, single derivative of x, single derivative of y, plus single derivative of z. Okay. What about del x, del cross? Yeah, it's a curl, right? So this tells you, like, I mean, they're really complicated. If you look at if you type curl math and then Google image, you can see some things that kind of help you understand what curls do. And they're kind of confusing. Basically, it's like trying to tell you which way a vector is rotating. That's kind of what it does. Whatever. You don't need to know any of this stuff. Okay, the theory of relativity is E equals mc squared, right? Right?
We already played this game.
Yeah, he was in my class. That is not what Einstein derived. That is actually wrong. E squared m squared c to the 4 plus c squared p squared. That's the actual equation. Notice that if, oh god, which one is it? Okay, if p is 0, then this reduces to equals mc squared. Okay, so only for an object not moving, p of course is momentum, mass, velocity. For an object not moving equals mc squared, and then the press like that because it's easy, but ultimately this is the correct equation. And you also get things like, well here, let me solve one of them. Okay, so for a photon, the rest mass is 0, so it doesn't weigh anything. Okay, so what you end up with is E, which of course for a wave is Planck's constant times frequency. And I have, in the exam, I haven't come up with the exams yet because I think the school's policies are going to be changing. CP, right? Is that right? What am I doing? Sorry. Yeah. Okay. So any equations you need, even dumb, simple ones that I kind of think you should know, it's okay. I have them on the cheat sheet. Okay. Anyway, so what I got confused was the frequency of light is the speed of light over the wavelength. Sorry, that should be there. This is therefore, so that means like the second step of the derivation. And therefore, if I solve P, I just divide out by C, so therefore P is H over lambda. Okay, so what really drove people nuts was that photons have no mass, but they have momentum. That should not be. Momentum is mass times velocity. Yet, for something specifically that has no mass, it still has momentum. No one really understands this, right? Just forget it, it's just crazy. I mean, I can mathematically prove it, but I don't understand why something with no mass has momentum, yet it's very observable. And I believe the photoelectric effect proves that, because when you hit a metal, so like it's a metal bar, it's in a vacuum, and light shines on it of enough energy, electrons stream off. You have to conserve energy. Anything that happens conserves energy and momentum. So if electrons are shooting out, they picked up some momentum, and it had to come from the photons, so the photons had to have momentum. That's what really confused people. So Einstein comes up with this, sure enough, photons have momentum. It all makes sense. So you can conserve energy and momentum at the same time. Actually, it also, if you ever wonder how do they measure Planck's constant, what you do is you look at the energy of electrons coming out of the metal versus wavelength. And of course, the higher energy, shorter wavelength that photons have, the more energy the electrons have. And so the slope of that line is h bar. That's where they come up with it. Anyway, now quantum mechanics, of course, is, what is very important is the eigenvalue equation. And I hope you remember this. This is a very generic form of the eigenvalue equation, where an operator, double derivative, it's just a double derivative, whatever, times a wave function. I know that you usually see psi for a wave function, but I usually try to reserve psi for the Hamiltonian. Hamiltonian operator, the energy operator, is very different and special. You always get a number, 5, times the wave function. And the Hamiltonian, of course, that eigenvalue, that number is the energy. And we think of the wave functions of the Hamiltonian as being different, as being special, those are the real wave functions. For other operators and their wave functions, they're useful, but they aren't necessarily reflecting reality like the Hamiltonian does. Anyway, that's the eigenvalue equation, and the damn thing better work. And here's the Schrodinger equation, which, by the way, no one really knows how the dude derived it. I'm going to write out the Hamiltonian operator because, again, that one's special. That's the one that everyone cares about. My handwriting will improve over time, by the way. I'm rusty. My handwriting will be much better in about 1 week. Okay. Oh, wait a minute. It would help if I had the constants right. Sorry. Catch me when I do that. That's one thing that's frustrating about any of this. If I'm missing a 2 or a minus sign, it doesn't work, and that can just drive you nuts. I try never to make a mistake. That's ridiculous, but I do try my best. Anyway, so that's quantum mechanics. Let me point out a couple of things. Again, don't forget that. Well, I'm actually going to tie all these together. That's why I'm talking about them. Okay, cool thing is, you may see it written about this, that this is the non-relativistic form of quantum mechanics. The way you know that is you don't see the speed of light. The theory of relativity has the speed of light in it. Any equation derived from the theory of relativity must retain the speed of light in it. It has to be there. Any theory, equation, anything derived from quantum mechanics must have an h-bar. So when you see an equation with h-bar, it's a quantum mechanical expression. If you see one with a c, it's a relativity thing. Now, the thing is that we should have an equation that has both of them, right? There are relativistic effects in atoms. Take a gold atom, right? It has a really, really heavy nucleus that's very positively charged. It turns out that the 1s electron is spinning really fast because it's, here's this positive core, it has tons of positiveness, and here's this electron right next to it. It turns out that that damn thing has so much kinetic energy, it's going so fast, that you actually need to use this equation. So if I'm describing an electron, I need quantum mechanics. But if I'm describing something moving fast quantum mechanically, I need to be using the theory of relativity. So we know that this is actually wrong. This is wrong, and we know it. It works really well for the first 3 rows of the periodic table, but is ultimately wrong. Because it doesn't have the letter C in it, and it needs to. Here's another thing, and you don't need to write this down. Okay, that's hydrogen 1s, H minus, right? Hydrogen has 1 electron, so H minus has 2 electrons. Here's the 1s orbital, and I put 2 electrons in it. Is that okay?
No, it's wrong.
It's wrong. You can't have 2 spin up. It has to be spin up, spin down. It has to be singlet. The Schrodinger equation doesn't prevent this. The Schrodinger equation is okay with that. The Schrodinger equation is okay for hydrogen, but as soon as you get beyond it, it fails. The Schrodinger equation actually has a lot of problems. And that's something, a lot of people don't learn that, especially at undergrad level. The Schrodinger equation is actually wrong. I actually will spend a day where I tell you what the real equations are, and actually I'm going to show you some of them today as well. Okay, so what I wanted to do is point out that no one knows where Schrodinger came up with this. I actually looked up his papers. He just kind of wrote this stuff down. But it turns out we think that he started here and that he inserted Einstein's relativity. Maxwell's equations are where you get the concept of waves. And then when you make it consistent with the theory of relativity, you can actually derive this. So we think Schrodinger did that, but we don't know because he didn't tell anyone. No one thought to ask, and he died. So no one knows. Okay, now if we start with Maxwell's equation. So Maxwell's equations, which no one ever questions. I just told you this is garbage. I don't think people understand this, and this always seems to be true. So no, I've never heard anyone say that Maxwell's equations are garbage. If you start with this, and this is related to your homework, by the way. Actually, I always put a bunch of hints. I put a bunch of hints in the problem set. The hints basically are telling you what to do step by step. So look out for that. I think I gave you enough hints on the homework to do number 1. But here's what you do. You start with this one. And the way you solve it, by the way, is you put one of these in front, and then you do that the same on the right, left and right, because of course you do. Okay, now this, of course, ends up being the, del squared. Now the way you do this one is I give you an identity on the homework. When you have a curl and a derivative, there's an identity. And from that identity, you can figure out what to do. It's just a bunch of algebra. All right, what you get from that is minus del squared E, and this is what you derive, is 1 over c squared, the change in the E. E here is the electric field, so not energy. There's not enough letters in in the English alphabet. Sorry. Remember, E is the electric field. You know, we use Greek letters a lot too, right? We read the math smart enough. Okay, now the solution to this, and I'm using 1D. The solution to this, I'm going to give you a more complex form than I did in that silly little textbook I wrote, is you give it some magnitude. He needs to have, electric fields have units of volts, I think. I'm pretty sure that's true. I should have looked that up for class. And unlike the textbook, my silly textbook, which is for undergrads, you should know enough complex mathematics to know that e to the I, blah, blah, blah. And in case you forgot, that's okay, I'm not going to leave you hanging. You should know that this is code word for cosine. Notice that it includes space and time because we think of waves as traveling, and traveling takes time, so there needs to be a time component. And of course, there's, you know, it exists over a finite space, so there needs to be a spatial component. So that's why there's x and z. Anyway, so e to the I, blah, 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 is cosine plus I sine. So anyway, just in case you forgot that, you do need to be, you need to be good with your complex math, and we'll be going over that in case you have some trouble. Okay, now, but we're going to stick with this, the top one, because it's easier. Okay, now what you do is I'm going to just work in one dimension because why not? It's just easier. Okay, so now if I plug this sucker in, and when you solve differential equations, and I'm going to tell you, we're going to have some time maybe at the end of the class. I'm going to go over some advanced techniques to solve differential equations numerically. Mathematicians like to put them this way. They like to have everything on the left equal to 0. That's just how they do it. So I just want you to see that because when you are Googling answers, you're gonna run into things generally put this way. Chemistry, we like to do it more like this. So right, I'm taking this, I'm bringing this over and setting it equal to 0 because that's what mathematicians like to do. I kind of like the fact that I should get 0 at the end because that's just like it'll be like easier to figure out whether I did it right. So that it has a little bit of appeal. Okay, now if you plug in this damn thing, you plug this damn thing into this, what you get is, where am I at? So you plug that into the, yeah, right here, which one? Minus k squared plus, anyway, so you're all capable of doing derivatives. My parentheses are not perfect and that bothers me. Now they're perfect. Okay, then I've got the wave equation is still there. Okay, so there you get it. Again, it is pretty simple. I just simply took this damn thing and I just did a double derivative in x and a double derivative in t, and I did some factoring. It's just algebra. A lot of this class really is just algebra hard. But it can be sometimes like a few pages of algebra, just heads up on that. But you learned algebra in middle school. Okay, so what? What do you get out of this? Okay, what you get is k, which by the way is, if you look at the wave equation, k has got to be 2 pi over lambda. So it's traditional to put, it's easier if you look right here. When a wave has traveled from 0 to 2 pi, when a wave has gone from 0 to its wavelength, cosine has gone from 0 to 2 pi, right? So if k is 2 pi over the wavelength, when x is equal to lambda, when x has traveled lambda, cosine has gone from 0 to 2 pi. So it makes sense. This is oddly equal to the momentum. It's related to the momentum. Sorry, it's not equal to the momentum. It's related to the momentum. Okay, and so this is equal to, sorry, where am I at? W over c, which is, of course, 2 pi times the frequency. Angular frequency is 2 pi times what, the normal frequency. another annoying little factoid that I wish we could get rid of. Let's see. Okay, so now what have I got? Okay, let's put those two together. And I have got C is lambda times the frequency. Okay, there we go. So now I know what the speed of light is. So part of what we do here is Maxwell's equations give us differential equations. Math textbooks tell us what the solutions are, E and EI, blah, blah, blah. You put the two together and then you get new things. Here now I know what the speed of light is. This is probably how they figured out what the speed of light was, by the way. You know, you're like, well, I know what the speed of light is. You know that because someone back in 1930 did this. So anyway, okay. Oh, God, no, where am I at? Okay, now let's start working with wave equations. Okay, now what I'm going to do is I'm going to start modifying this. I'm going to start calling it, instead of E, I'm going to call it psi. So what I'm going to do is I'm going to start converting this equation for a photon. I'm going to start converting it to an equation for an electron. And I'll explain why I think I can do that. So let's go from, I like to use EXP for exponential when it's kind of long. Okay, so there's that, which I already wrote. And what I'm going to do, and this is kind of silly, I'm going to divide out h bar, and then I'm going to multiply by h bar. And h bar, of course, is h over 2 pi. And angular frequency, omega, is 2 pi times the real frequency. So don't forget that this is h bar, and this is, I want to make sure that you don't get confused in a step. You know, wait, where the hell is that from? Where's omega? Right, it is omega. That stuff can completely throw you off if you get a little bit lost. Okay. Now, notice that, okay, what is all this? Let's see, this ends up being, H. Right, what's H nu? H nu is what? Yeah, it's the energy. Yeah. And H bar K, by the way, that ends up being momentum. And you can prove that from remember the momentum of, well, here, let's do it. Okay, so h bar is h over 2 pi. Sorry if I'm writing a little small. K is 2 pi over lambda. So this ends up being h over lambda, which is momentum. Right, this is momentum. So notice that you've got this thing with momentum and energy in it. Okay, so what? Okay. Now, since I'm going to write down the Maxwell deal again, the Maxwell's differential equation. What I'm going to do is figure out that what I've got is minus 1 over h bar squared p squared minus e squared over c squared. Wave equation. So I'm just, most of it's writing stuff down that I already did. Okay, so here's what you got. So again, I've just done some manipulations. I multiplied and divided by h bar. I've noticed that momentum has popped out, energy has popped out, so that's why I'm writing that px minus dt. I put it into this deal. Again, derived from Maxwell's equations, and now what have I got? Well, this part has to be 0, right? So therefore, P is equal to E, did I do that right? P squared is equal to E squared over C squared. Therefore, sorry, E is energy. Oh, God, I'm sorry about that. I hope I'm not losing you there. we have two E's. We have E for an electric field and we have E for energy. I hope it's not too confusing which one's which. You may have some trouble with your notes, but then that's why we have class. Okay, and what's that? If you look at top, if mass is 0, E squared is C squared D squared. Right? It's the energy of a photon. But I'm kind of describing a photon. Okay, I'm almost out of time, so let me just finish up with one last thing, and we'll continue. I always review a little bit about what I did the day before I began a class. So I'm mostly at the end. So we think Schrodinger did this. What I just did here, we think Schrodinger did as well. So what comes next is, okay, what you now want to do, okay, you see how I've got P squared minus E squared over C squared? Look at that thing. That's basically, we're awfully close to this. So I got C squared, P squared, plus M squared, C to the 4, right? Okay, so here's what you do. This is so clever. All right, so minus 1 over h bar squared. So what you do is you reverse engineer it. Now, there's some algebra here. Don't even worry about it. Now, again, I don't want you trying to memorize this for an exam. I'm not going to put this on an exam. I'm just going off in a different world. I just want to get you immersed in this stuff, and I thought this would be the quickest way to do it. And then I'm almost done. Because I'm actually, what I'm lecturing off is on a paper, and as soon as the website is up, I'll put the paper up, and it also has some historical context about who all these people were, which I think is kind of nice. Okay, so what you've done is you've inserted this. Now, reverse engineer. What equation, what wave equation, what diffie-q would have made this happen? Oh, that's not hard. That's not hard to figure out. It ends up being del squared. I'm going to introduce a little layer of complexity in terms of math speak. Here's C squared. Okay, here's the wave equation. Again, I'm calling it a wave equation instead of an E because we have too many E's. That, and I'm trying to describe matter. Because the way I'm describing particles now is because I put that m squared c to the 4th, c, that term. Again, there's been some manipulation of the algebra, by the way. So, okay. Okay. All right, so this is actually really all I wanted to get to. This is called the Klein-Gordon. Okay, this is actually the Schrodinger equation that's consistent with relativity. And it turns out not to work. So Schrodinger equation developed the Schrodinger equation 1920 something. About just a few years later, people realized, wait, no, there's no relativity into it. Somehow it's not there. And so when they tried to put it back in, they derived this. Now, it turns out it doesn't quite work. It doesn't describe electrons. It doesn't work for electrons. It's the weirdest thing. It's the weirdest damn thing. It describes bosons, like the Higgs boson. It will describe that, but it will not describe a lepton. You know leptons. An electron's a lepton. It doesn't describe an electron. Okay, the solution, by the way, was instead of working with this, E squared equals blah, the solution is to take the square root and make some approximations, and then what you get, the derivation from here to here, assuming that you're going to work with the square root of energy, instead of just energy. When you insert this into here, the derivation is a bit of a pain, but what you end up with is this. again, that's energy. They also figured out that, like, well, if that's energy, you had to throw in potential energy too. So, and that's the Schrodinger equation. Anyway, I know I went a little too fast here because I'm out of time. I've gone over. So I'll start here then, and I'll tell you a little bit more about how to get to the Schrodinger equation, and then we'll start doing some more interesting derivations. We'll get back to your undergrad stuff. So anyway, again, you don't have to memorize any of this. It's just kind of for fun. We've got plenty of time to be immersed in unbelievably hard mathematics, which is what we're going to be doing for months. So anyway, yeah, you all okay? I'm going to come over and breathe on all of you. So